Okay, so here's a scoop. Put this down. This is your cheat sheet. If you're good at math, basically, if you've got a satellite here, okay, I'll call this the satellite mass. Okay, it's got a velocity. It's got a central body. I'm going to call this the mass of the satellite. Okay, I'm going to call this the mass of the central body. Yeah? First part of Brennan's name, right? Okay, it is some radius r. It also moves around with a period t. So there's two different options for us, right? But generally what we do is we say that the centripetal force, okay, the m of the satellite, right, the force needed to make this satellite go around times its velocity squared over r. Isn't that the formula for centripetal force? Yeah. That equals of course, it doesn't matter which order you put these guys, right? Here, there I have S and C, but here I put C and S because there it is, right? Over R squared. Now, we are assuming a lot of things here. We're assuming that inertial mass is the same as gravitational mass, and this is pretty good, right? The mass that's in gravity formulas is the same as the mass that's in F equals ma. We're okay with that, right? The second one, and this one's a little bit dodgy, is that this satellite goes around a circle that has the same radius as the center-to-center distance of the masses. Doesn't that mean that the Earth does not move because the satellite's going around it? Doesn't that mean that? Because if they had the same mass, they actually wouldn't orbit, one wouldn't orbit the other. What would they do? They could still orbit each other, but they wouldn't orbit, one wouldn't orbit the other. If they had the same mass, they would orbit each other about a spot that is, what do you think? One, here's the other, same mass, right? What are they can orbit each other and go around and around, but what are they going to orbit? Around the center of mass, yeah, the point at which they would balance. So if one's a bit more massive, it would orbit a little closer to that, right? Okay, so we're assuming that these satellites, whatever it's orbiting for the stuff we're doing, and don't worry, I'm always going to give you things that this works for, okay? But we're assuming that these satellites have insignificant mass compared to this. Is that true for the moon? Well, kind of. The moon is actually about a little more than 1/100th the mass of the Earth, right? It's 7.36 times 10 to the 22nd. The Earth is 5.97 times 10 to the 24th, right? And so the moon actually makes the Earth move a lot. We move about 10 meters per second because of the moon's motion. The moon is moving about 1,020 meters per second because of its motion. This causes the water on the Earth to slosh around. So there's tides, there's two tides, one toward the moon and one away from the moon. And we'll talk about that, but that's caused by the Earth moving. The Earth moves away from the water, okay? But anyway, that's, you know, way beyond the scope of things. This is one orbital condition, okay? And if you can just solve this, if you can solve that mathematically for all the things that you could solve for, that's all you need, but we'll solve this. And then the other orbital condition is that we just, instead of using v squared over r, we use the 4 pi squared r. So mass of the satellite, 4 pi squared r over t squared is g, mass of the central body, mass of the satellite over r squared. So this is the second one. Now, how are we at solving for things inside there? It's always the same thing. It's always cross multiply. Okay? It's always cross multiply. It's always divide, unless you happen to by cross multiply and get the whatever it is alone. It's always divide, and then it sometimes is a root. You have to square a root, or 2, or maybe 3, right? It could be a square root, it could be a cube root or something like that. In the worst case scenario, we could get up to a cube root, but there it is, right? Okay. Sometimes we don't need to do that, but when we divide, we end up with what we wanted, okay? Okay, so let's look at this one. Example. What is the velocity of orbit 250 miles above the Earth? This is where the space station is. The space station's height varies. They'll push it out really far, and then it's, it kind of encounters a little bit of atmosphere out there. Not much, but enough to slow it down. So it spirals in closer and closer to the Earth. Then they'll push it out. and it'll spiral in closer and closer. If they put it far enough, it'd orbit forever like the moon, but, you know. So 250 miles above the Earth, what do we have to do? 250 miles is no good, right? So don't we have to convert miles to meters? Isn't that right? And a mile is 1,609 meters, I believe, isn't it? Because if you run a 1,600, you haven't really run a mile. You're 9 meters short, right? Some crazy thing, right? So the first thing I want to do is I want to go 250 times 1,609, I think is what it is, and get the meters that it is above the Earth. So 250 times, and this is, my calculator is in permanent scientific notation because there's either that or no scientific notation. It shows me like 12 digits, right? I hate these things. Okay, 225 times 10 to the 5th meters. Yeah. Is that the radius of this ship's orbit, or of the space station's orbit? Or is that just how far it is above the Earth? What is the radius of the Earth in miles? Do we know? This distance here is about 4,000 miles, yes? Yes? Okay. And so the space station is 1/16 of that out farther from the Earth, right? It's like, is that the radius of its orbit? Here's the space station. Doesn't the Earth look big when you look at the space station pictures? How big is the Earth? It's a big Earth, isn't it? When you see those pictures, you can tell it's curved, but it's a big Earth, right? So you're like about a 1/16 of an Earth radius above the Earth, right? So what is the radius of, what do we have to do to find the radius of its orbit? We want the center to center distance. Do we need to add the radius of the Earth? Yeah, that's what we need to do, right? Because we are really what we're dealing with, like there's the Earth's surface, right? Right? Here's the orbital trajectory. It's really not that much farther. This is the 250 miles, right? Okay, so it's really, you know, basically it's almost at the surface, but just a little bit more, right? Okay, so what's the radius of the Earth? We've got to figure out what r is. All this work to figure out r. 4,000 miles. Yeah, I know, but let's go with isn't it 6.38 times 10 to the 6th, right? Plus 0.40225 times 10 to the 6th meters, right? This is what you're supposed to do. I don't know if you did that in like elementary school or whenever you learned scientific notation, right? You're supposed to put them in the same scientific notation. These are the same number, aren't they? I believe, aren't they? Yeah. What is that going to be? That's going to be the distance to the center of the Earth. This is the distance to the surface. This is the distance from the surface to the center. So the radius of orbit is both, right? Yeah, the sum of them. So I'm getting the radius of orbit is 6.78225 times 10 to the 6th meters, yeah? That wasn't the question. It was like, we should be done now. Dang. Oh, it's fun. That's like saying weightlifting isn't fun. Oh, this isn't fun. I'm not going to do it. Come on, man. Where's the team spirit, you know? You suffer pain so that you can get paid more than minimum wage later. Okay, so so now we're ready to go. Which of these are we going to use if we want velocity? We're going to use the one that has velocity in it to find velocity, yes? Doesn't that make sense? So let's take this one. Let's solve it for v. Now, I'm going to always do this. If you look at these things, notice that the mass of the satellite is on both sides. Do you notice that? The satellite mass always cancels. You can cancel it right off the bat. This is good news for us. This means that, what? Say it again.
How come, like, what's the point of even having, why don't you just do like v squared over r?
Oh, I could do that. Yeah, that'd be fine. But this is nice because this is centripetal force equals force of gravity. So, I mean, logically it makes more sense, right? Okay. So, I'm going to cross these guys out. And then what's our first step? Our first step is to cross multiply. And if you really forgot all your math, that means that the next step is is v squared times r squared.